Hello everyone, my name is Gomes and I'm a PhD student in IRA program at Faculty of Engineering of University of Porto. This presentation is about a preliminary numerical study of my research project which has as main goal the fatigue assessment of suspension components in freight wagons, mainly the leaf springs. In summary, this work is divided in 6 points. First, introduction and objectives of this research work. Second, material characterization and a geometrical model. Third, numerical model and the assumptions considered in numerical analysis. Fourth, fatigue assessments based on SWT curve. Fifth, estimation of classical Hessian curve, and finally it's presented some concluding remarks. Over the years, railway sector in Portugal has suffered a significant shortage of resources, generating many issues associated with maintenance of the rolling stock, affecting its operationality. Scientific works regarding prediction of fatigue is still studied in order to improve the fatigue resistance in railway components. One of components more subjected to fatigue are the leaf springs that constitute the bogie suspension of freight wagons. The failure of springs have generated derailments. So, in order to reduce these issues, this research work intends to provide new tools for fatigue prediction, which are an important thing to assist the maintenance process of the rolling stock. Steel grade which constitutes the leaves is a spring steel denominated as DIN 51 SE7 with high yield tensile stress. Regarding geometry of spring, leaf springs according to UIC 517 OR standard with 16 mm thick, 120 wide, 1190 long and 8 leaves. About numerical model, we used a finite element method with ANSI software. We consider only a quarter of a real model with quadratic elements. Each element was modeled with an average size equals 5 mm for spring leaves and 8 mm for the rest of components, spring buckle and taper key. We consider all 4 elements a long thickness for each leaf. About mechanical behavior, spring leaves was modeled as isotropic elasticity, and its plasticity was modeled by a bilinear kinematic hardening model. While for spring buckle and taper key, the isotropic elasticity was only considered. About contact, we considered the frictional model with a friction coefficient equals 0.2. This figure presents the whole boundary conditions, the symmetry boundary conditions, and the place where a force is applied for mounting and for cyclic loading, and this point it, it was the place where the structure was fixed. First load step is about clamping by spring buckle, while load step 2 is about leaf spring mounting. Regarding load step 1, clamping force was modeled by rotation elements applied on middle of the spring buckle, which a force equals to 50 kilonewtons for a quarter of model. For load step 2, we applied a mounting force here, trying to simulate the real boundary conditions as illustrated here. The force applied was equals to 10 kilonewtons, because we only consider the half of total cylindrical area. About third load step, we simulated 3 cyclic loading levels, low, medium and high, based on this numerical total bending test. This picture shows the boundary conditions used to simulate the cyclic loading levels. After simulating our model, we can predict the fatigue life by using SWT life curve, equation 1, where the coefficients and exponents may be estimated by hardness model, where the hardness of springs can be approximated by this formula. As a result of this calculation, we obtain this SWT life curve. About Sean pinning process. This process is often applied, at least on leaf spring surface, under tensile states, taking into account the hardness of our springs. We can consider this distribution near the top of surface if the shot pinning process at room temperature is considered. For considering this effect, we use the superposition method for estimating the fatigue life. Now we can analyze the fatigue behavior of each leaf spring for each loading level. First, we consider the load level, and we are analyzing the SWT per meter, where we can see that the maximum SWT per meter occurs for spring 8 and spring 7. The difference is not so high, but we can see from these pictures, A for spring 7 and D for spring 8, which there is a hotspot stress on surface of spring 8. This picture shows the, dist the distribution of SWT for each leaf springs. Now, now analyzing the median loading level, we can see which for the last two leaves there is a greater increase of SWT parameter when comparing with others, the first ones. We can see here from comparison of 7 and 8 springs leaves, which the difference is not so high as well, but the leaves on surface of spring 8 there is a hotspot stress as well. Now, analyzing the high loading level, we can see that the highest SWT parameter occurs for spring 7 instead of spring 8. But there is a difference. Now we can see there is no hotspot stress on leaf spring 8 surface presented here. After analyzing each loading conditions, we can conclude that the critical places are on leaf spring 7 and 8 by analyzing the SW parameter. But now we are understanding what are occurring with these points. So first 2 points are D and E. Well, these points correspond to leaf spring 8, and we can see that there is a hotspot stress because there's an abrupt variation of contact between leaf spring 8 and spring buckle. That increases the stress. Then we can try understanding what these are happening. So after analyzing the stress, the equivalent stress, we verified that the equivalent stress is higher than yield stress. So the plasticization that occurs induces different behaviors on each leaf spring. Well, we can see that stress here is higher than this point. So after this whole, we decided to consider the leaf spring 7 as a critical element because there's not a pure hotspot stress despite the plasticization for loading conditions. Yes, the plasticization induces problems in the use of the superposition method. Well, now we are trying to predict the fatigue life for each loading level. We can see from SWT life curve that for load levels the fatigue life is infinite as presented here, while for high levels the fatigue life is on low cycle fatigue. Now, considering the shot pinning effect by superposition method presented by this equation, we can see that there is an improvement of fatigue behavior around 10 times than without shot pinning effect. Lastly, we want to estimate the Hessian curve. For that, we need to calculate the nominal stress range, and one formula to relate the force range and stress range is presented by equation 2, that is the definition of normal stress for a straight beam, which is splitted by splitted the total force range by the number of waves. Then we need to calculate the nominal normal stress range for the same stress ratio. For that, we can use this equation 3, where the function f is given by equation 4 for stress ratio greater than 0.0. As a result of calculation by equation 2 for free levels, we obtain the nominal stress ratio, and we can see that there is difference between stress ratio for each level, but the difference it's not so high, but it's normal because there is always a previous loading because the mounting of these springs. Then we need use the equation 3 and 4 to estimate the Hessian curves for the same stress ratios. So by using that those equations, we can obtain this data, and we can draw this graph where this is this equation for R for stress ratio 0.5, 0.1, and 0.0. With this work, we can conclude that the critical seats occur for leaf springs 7 and 8, considering the SWT parameter, the existence of hotspot stress, which is due to an abrupt variation of contact geometry, increases stress and consequently increases the uncertainties of the model. However, the difference of SWT parameter in critical leaves is not so high in low and medium loadings. On the other hand, for high levels, we, 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 we verify that the plastification occurrence that decreases the stiffness of leaf 7 and 8 and increases the longitudinal stress on leaf 7. The shot pinning process is beneficial since it increases the fatigue life around 10 times than without this mechanical process. And after leaf spring mounting, leaf springs work in a stress ratio around 0.5. As feature work, I will characterize the leaf spring material better in terms of fatigue, and then I want to analyze the fatigue behavior of these leaf springs in real operation conditions. These are references used for this work. Thank you for watching.